Welcome back to our lecture series on 8085 microprocessor. So in this video, we'll be discussing the various interrupts of 8085 microprocessor. And so we all know what is a interrupt. Hmm, as it's a very simple process, like something that interrupts the main program as an interrupt. So let's say, or something that interrupts uh, the main flow of anything. You're doing something, someone comes and interrupts you. That is very similar to an interrupt. Or let's say, in terms of your PC, uh, the mouse, when you move the mouse, let's say you're making this line over here, right? This goes into the PC as an interrupt because it's causing interrupts to the main flow of the main program. Everything like let's say you're using a smartphone. When you click an icon, that goes into the uh, processor as an interrupt, or you double tap your screen, or anything of that sort goes into the processor as an interrupt because it interrupts the main program that is continuously running. Uh, so let's say, and interrupts are very similar to your the execution of interrupts are similar to your functions. Let's say, let's look at how interrupts get executed. So let's say this is your main program. You have a lot of instructions, and suddenly there's an interrupt over here, right? So let's say you were executing the instruction over here, and suddenly there's an interrupt, a hardware interrupt that has occurred. And what happens is that your uh, processor will stop the current execution of the main program and goes into something known as a ISR. ISR is nothing but a subroutine. It's very similar to a subroutine. So so here what happens is that these are a certain step of this set of instructions that is used for servicing a particular interrupt. So every interrupt will have its own ISR, interrupt service routine. It is known as interrupt service routine. So there will be a set of instructions which will get executed, and then after that it will come back on return instruction. It will come back to the main program where it left. So for reaching the main program where it left, it has to push the program counter. Why do you push the program counter? Because program counter will be having the address of the next instruction. So it will be pushed to the top of the stack, and then the new address, the address of the ISR will be taken into the program counter, and it will start execution of the ISR, interrupt service routine. And then once it is done with the interrupt service routine, it will reach the return instruction and come back to the main program and continue its process. So this is the very simple process of a interrupt. Whenever you interrupt the processor, it stops the execution of the main program, goes into a ISR, interrupt service routine, services the interrupt that has occurred, and then it comes back to the main program. That is the course of, that is how interrupts are serviced. So this is very similar to how a function is called or a subroutine is called. So that is what a subroutine is. Basically, you are writing a instruction, call instruction, and you are going into a function where you execute a set of instructions. But here, it can be soft instructions like software interrupts. I will be seeing what is a software interrupt, or it can be hardware interrupts. If it's a hardware interrupt, it means that the interrupt is coming from an external device, and you'll have to service that interrupt. So here, sorry, here let's look at the various classification of interrupts, right? We have two classification of interrupts. There's the software interrupt and the hardware interrupt. Now, software interrupt means we are writing instructions in order to produce an interrupt. So as a programmer, you can write instructions like RST0, RST1, RST2 up to RST7. These are all the software interrupts of 8085 microprocessor. These are instructions basically. RST0 is an instruction where in which the program counter will directly go to a memory location called 0000, and it executes whatever instructions that you have written over there, and it comes back to the main program. Now, these are the addresses that we have written over here on the right. So, when these interrupts are occurring, the program counter goes to these addresses directly, and it executes whatever the instructions that are there in these addresses and comes back to the main program. Now, this is very similar to your call instruction. So in call instruction, what happens is that you give a call associated with a 16-bit address. So which means that this is a 3-byte instruction. You can say this RST0, RST1, RST2, these are all 1-byte instructions because the addresses are fixed. You can't change these addresses for RST0, RST1, RST2. So these addresses are fixed, and therefore the processor, whenever it gets this instruction, it directly goes to this address. So which makes it faster than a 3-byte call instruction, RST0 to RST7. These are call instructions, or you can also call them as software interrupts. And you can go to these locations, and whatever instructions you want to write in these locations, depending upon that, certain functions will be done. So this is very similar to your functions or subroutines, your software interrupts. So there are 8 software interrupts. These are the addresses of the ISR. So this is the address of the ISRs. So I hope in the ISR we write the instructions that has to be executed when these software interrupts occurs. So basically we write it as part of the program, very similar to a call instruction. Now these addresses are very easy to remember because you just have to multiply these numbers with 8 to get these addresses. So 0 into 8 is 0, that's 0000. 1 into 8 is 0008. 2 into 8 is 16. In decimal, in hexadecimal, 16 is 10. Similarly, 3 into 8 is 24. In decimal, which is 18 in hexadecimal, RST4 is 4 into 8, that is 32, which becomes 20 in hexadecimal, 32 in decimal. Similarly, and so, all the addresses you can easily get just by multiplying these numbers with 8. It's a very simple technique to remember the vector addresses. So that is all about software interrupts. Software interrupts are very similar to your subroutines. You just have to write some instructions for servicing these software interrupts. Basically, you write these instructions for performing certain functions, similar to your subroutines. So the only advantage is that a call instruction is a 3-byte instruction, whereas a software interrupts RST0, RST1, these are all 1-byte instructions. The execution becomes much more faster than a call instruction, which is of 3 bytes. So that is the difference. Now let's go into the next classification, that is your hardware interrupts. So in hardware interrupts, there are 5 different interrupts in hardware interrupts, which is your trap, RST 7.5, 6.5, 5.5, and INTR. So the on the right we have given the address of the ISRs. So these are the address where you can write the corresponding ISR, address of the interrupt service routine. Interrupt service routine is nothing but the set of instruction that has to be executed when these interrupts occur. So one thing you might be noticing is that you have an address like 0024 over here, and we have something like 0028 for RST5. So there are only 4 memory locations for this interrupt. So 4 memory locations are more than enough because in 4 memory locations you can write a long jump, as well as you can also write a return instruction. So your interrupt service routine might be at a different memory location, because when such a interrupt occurs, it goes to this memory location, and at this memory location you might be giving a jump instruction where it goes to another memory location, and from there you can return to this location where it has a return, or you can directly return from that point to your main program, however you wish it, however you want to do it. Now, there are five hardware interrupts. These are basically five pins on your 8085 microprocessor, physical pins. So onto these five physical pins, you can connect various devices, whatever device you want to connect. So the other thing is that you might be wondering why there's only five devices. So it's not exactly five devices. On the first four interrupting pins, you can connect up to four devices because these have a specific address. So in these addresses, you can write only the interrupt service routine corresponding to one device, and therefore you can only connect four devices in these interrupting pins. But your INTR, the last interrupting pin, INTR is a non-vector interrupt, which means that there is no specific address that is given and that is already assigned to this interrupt, which means that you can connect up to around, if you are using a 8259 uh, programmable interrupt controller, you can connect up to 64 interrupting devices in the cascade mode. We will be discussing about 8259 in detail. So, uh, which means that uh, you can connect up to 64 devices into this INTR pin, as well as whenever a device interrupts the processor, it also gives the address, the vector address of the ISR, so that it doesn't has to go to a specific address, because at one address, like at a specific address, you can only write the interrupt service routine for a single device. So this is the major advantage of having a non-vectored interrupt. So vectored interrupt means you have the address already, I mean you have already assigned an address. So there are two types of another classification of interrupt is vectored and non-vectored. Vector means the address of the interrupt service routine is already assigned, which means that you don't have to give an address when the interrupt occurs. It directly goes to the assigned addresses like this 0000 or 0024 or 0036, which is over here, or 0034 to see, these are all already assigned addresses. So whenever these devices interrupts, which are connected to RST 7.5, 6.5, or 5.5, it directly goes to these addresses and start executing the interrupt service routines. But for INTR pin, there is no address. There is no pre-assigned address. It's a non-vector interrupt, which means that whichever device is interrupting the processor through INTR pin, it can give its own address. So we already know what is an ISR. ISR is basically a driver software kind of a program, because each device requires some driver softwares or some set of instructions to service its its needs. Let's say you're typing something on the keyboard. So the processor should understand which key is being pressed. So basically, you need to send some data, or the processor should identify which key is being pressed, and depending upon that, it has to display the particular key, or it has to store that particular character into the memory in the form of ASCII codes. So for that, definitely you need some program to identify what is the key and what has to be done corresponding to each keys, right? So that is your ISR, or that is what is your driver software. So it is the same thing that happens over here also. So here there are five hardware interrupts: trap, RST 7.5, 6.5, RST 5.5. Here also you can get the addresses just by multiplying the number with the numbers over here. The RST 7.5 with 8. If you multiply 7.5 with 8, you get 60. 7 eights are 56.5 into 8 is 4, which is 60. 60 is 3C in hexadecimal. Similarly, 6.5 and 5.5, all these numbers you can just multiply it with 8 and you'll directly get the address. Trap is also known as RST 4.5. In many books, you will see it as RST 4.5. It is either called as trap or it is either called as RST 4.5. So, yeah, so 4.5, if you multiply with 8, you will again get 24 in hexadecimal number. 4.5 into 8 is 36. 36 in hexadecimal is 24. 36 is the number in decimal system, but in hexadecimal it becomes 24. So that is the various hardware interrupts of 8085 microprocessor. Now there is a priority order for the hardware interrupts. Trap has the highest priority. This is the highest priority interrupt. The next priority interrupt is RST 7.5. Then comes your 6.5. Then comes your 5.5, and finally comes your INTR. So this is the order of the priority. First comes your trap, then comes your RST 7.5, then comes your RST 6.5, 5.5, and INTR. Now, except trap, all the other interrupts can be disabled. You can use an instruction uh, called DI. DI stands for disable interrupts. EI stands for enable interrupts. The two instructions, DI and EI. DI will disable all the interrupts except your trap, and EI can enable back all the interrupts. Now there is a very prominent reason why we can't disable trap, because trap is an interrupt which is kept for an emergency. Let's say this 8085 microprocessor is used for some particular application in an industry, and let's say in case of an accident, so and so function should be done, or you should directly shut down the system or something of that sort. So this can this interrupt should never be disabled at any cost. So that is why trap can never be disabled. All the emergency functions, like at a particular emergency situation, a particular function should never be disabled. So that is why we have this interrupt called trap, which is the highest priority interrupt, and it can never be disabled. So whatever is the case, this if trap occurs, if there is an interrupt on the trap pin, then it has to be serviced at any cost. Uh, so all the emergencies are always kept onto this pin, so that even by mistake you can never disable this interrupt. So I hope that's enough for the interrupts of 8085. So there are, let's have a small recap. There are two classifications of interrupts. There are software interrupts and hardware interrupts. Software interrupts are basically instructions. RST0, RST1, these are all instructions that you can write. And correspondingly at these memory locations, you can write the interrupt service routines for corresponding instructions, similar to a call instruction. You can call them at any point in your program. And whatever instructions you write in the corresponding addresses will get executed and come back to the main program when you give a return instruction at the end. Then you have your hardware interrupts. There are five hardware interrupts. trap, RST 7.5, 6.5, 5.5, and INTR. These are basically physical pins on your 8085 microprocessor, and you can connect various devices or various devices to these pins, and trap has the highest priority. Then comes your 7.5, 6.5, 5.5, and INTR. In the first four interrupts, you can connect only one device for these pins because you have only one address for servicing these interrupts. The addresses are fixed, so you can connect keyboard and mouse to the same interrupting pin because the interrupt service routine for keyboard and mouse will definitely be different. So you can write a single program at the interrupt service routine for keyboard and mouse. So definitely you will require two different pins for connecting the keyboard and mouse, but INTR doesn't have a address. I mean, there is no pre-assigned address for INTR. Whenever the interrupt occurs at INTR, the device itself gives the address to the processor, and therefore you can connect up to 64 devices using a programmable interrupt controller at this pin in the cascade configuration. So that is the advantage of this pin INTR. It's a very useful pin because in the first four pins you can connect only four devices, but in the last pin you can connect up to 64 devices in this pin. And the priority levels are from 1, 2, 3. Trap has the highest priority, then comes 7.5, 6.5, 5.5, and INTR. You can disable all the interrupts except the trap interrupt. You can never disable the trap interrupt because it is kept for emergencies. So that's all for this lecture. Thank you and have a nice day.